Hello. Today in this segment on my series of enzymes, I'm going to talk about how enzymes work and also how the substrate concentration, temperature, and pH can affect the rate of catalysis or the rate that an enzyme can do its job. So first, when we're talking about how enzymes work, there are two ideas. One is older than the other. So historically, the lock and key model is how we thought enzymes worked. And the idea is that the enzyme is a rigid structure and the substrate would fit into it like a key would fit into a lock. And we have discovered that enzyme molecules are not really rigid like locks and they can actually move. So a more updated model of how enzymes work is called the Induced Fit model. And it involves the substrate or the active site changing shape before and during and after catalysis. So the Induced Fit model looks something like this. So here you can see the shape of the active site and the substrate goes in and it just kind of wraps itself around it. This is the most accepted view. And on the next slide, I have a couple of GIFs that kind of show that in action. So both of these images, you can see that the active site, which is right here on the left image, and it looks like we've got two regions that are moving. On the image on the right, it looks like it's moving where the substrate's coming in and then it's coming out the other side. So you can see that movement taking place. It's just kind of wrapping itself right around the substrate. So that is the Induced Fit model. When we talk about how fast an enzyme can cause catalysis, it's based on a couple of things. Number one is how much substrate there is. And number two is the efficiency of the enzyme. So some enzymes are very, very efficient and they work very, very quickly, and others are not as fast. So one of the most efficient enzymes that we know of is catalase. We've talked about this one before. This is one of the oxidoreductase. This enzyme involves oxidation reduction occurring when hydrogen peroxide is broken down into water and oxygen. And it can break the hydrogen peroxide down at a rate of 1 × 10⁷ catalytic events per second. So the number of substrate molecules of an enzyme can react within a given amount of time is called the turnover number. And each enzyme has a specific turnover number and ideal conditions, and different things can affect those conditions, like how much substrate there is, the temperature of a system, and also what the current pH is. So when we're looking at the substrate concentration, if there is a low amount of substrate, the enzymatic activity is going to be pretty slow. So the reaction rate is directionally proportional to the substrate concentration at lower concentrations. So here, as we get more substrate, our catalysis or our enzymatic activity goes up because more enzymes are reacting with more substrate and we're getting faster product. And as they're filling up, there are going to be fewer and fewer sites available. So we get to a spot called the maximum velocity. And as those active sites start filling up, we're going to slow down the output of the enzymatic activity. And eventually all of those active sites get occupied. And we're at our maximum velocity for that particular enzyme. Another thing that we can consider with enzymes is how pH affects an enzyme catalysis, and each enzyme is highly dependent on a specific pH. And it varies slightly for each enzyme. Generally, it's going to be within what our body temperature is, and also wherever the enzyme is in your body, depending on what type of body fluid it is, what the pH is in that particular fluid. So pepsin and trypsin are both enzymes that aid in protein digestion. So one of their roles is to break that peptide bond holding the amino acid residues together. Pepsin initiates that digestion in the stomach, so it will work under best optimally at a pH of 2. Trypsin acts in our small intestines, and it undergoes its best enzymatic activity at a pH of 8 in basic conditions. Now, if we get pH ranges outside this optimal range, we might denature or unravel the enzymes, and they won't function anymore. So here are the examples of pepsin and trypsin. You can see that the optimal enzymatic efficiency is, or reaction rate is around 2 for pepsin and around 8 for trypsin. And you can see that as the pH increases here and it becomes more basic, the pepsin can still do its job, but there is a point here where neither pepsin or trypsin will be able to catalyze that protein and start breaking it down into the amino acids. Another thing that's important for enzyme catalysis is temperature. And all reactions will show fewer interactions under cooler temperatures. There will be fewer collisions, lower energy, and slower reaction rate. It doesn't matter if they're enzyme catalyzed or sped up or not. It's just the nature of chemical reactions. They tend to slow down when the temperature is low. And as temperature increases, the collisions start to increase, and there's more opportunity for reactions to take place as in the case of enzymes, as the enzymes and substrates are interacting with each other. But if the temperature gets too high, it's not like oh, we're just going to keep raising the temperature because that's going to make everything go faster. Well, if it gets too high, it gets to a point where it just unravels that protein completely. It denatures it. So in this image, you can see that the body temperature is around 37 degrees Celsius, and a specific reaction is going to be pretty slow with these cold conditions, just because there's not enough energy to have the collisions necessary for the reaction to take place. And as it heats up, you can see that the reaction rate increases, but if it gets too warm, the protein will just unravel and you see this sharp decrease because it can't function anymore. So this is a problem that can occur when people's fevers get too high. When people's fevers get too high, some of the proteins in their body can become denatured and seriously interfere with the bodily functions. So that is one of the dangers of having an extremely high fever for an extended amount of time. So that concludes today's discussion, in which I talked about how enzymes work and the models of the lock and key model and then the induced fit, where the enzyme changes shape. That's the most accepted. And we talked about how substrate concentration can affect reaction rate. If we have low amount of substrate, the reaction rate's going to get low. Eventually, though, as the substrate concentration increases, we're not going to keep going faster and faster and faster because all of the enzymes are going to get used up. And enzymes work specifically under particular pHs, and with outside of those ranges, they can become denatured. And enzymes also function within specific temperatures. And the cold temperature doesn't necessarily affect the enzyme performance, other than it just being really slow because of the lower amount of energy, the fewer collisions. But when we get beyond a certain temperature, that protein unravels and becomes denatured, and it just no longer functions. So in the next installment, I'm going to be talking about enzyme regulation, how it can start and slow down, speed up, stop. So thanks for watching.